Today we'll be measuring the efficiency of a PWM inverter drive. We'll be utilising two instruments today, the PPA1500 for the input power and the PPA5500 for the output power. We will then synchronise these two instruments in software to provide us with an efficiency reading. Hello and welcome to this presentation discussing the various challenges posing the engineer when making power efficiency measurements of an inverter drive. We're going to discuss measurement of the input, whether it be AC or DC bus, and then we're going to discuss the three-phase output of the inverter drive going to the motor. Today we're not going to concentrate on the mechanical power, so the speed and the torque, but we're going to talk about electrical to electrical power efficiency measurements and how we do this measurement using the Newton's fourth power analyzers. Today, as you can see, what we've got is we've got a PPA1500 measuring the AC input of this single phase input AC to three-phase output AC motor drive. We're not measuring the DC bus today, but we will be discussing that measurement. Then we've got the larger analyzer here, the PPA5500, which is our top spec analyzer, measuring the inverter output, which is of course going to include the distorted voltage and somewhat of a noisy current signal. This poses various challenges for the analyzer, and throughout this presentation what we're going to do is discuss both the input, the output, synchronizing the measurement, and what considerations as an engineer you must think about when selecting an analyzer as to how we think this analyzer is going to cope with the challenges posed by such a signal. So we're going to discuss how the PPA55 here copes very well with common mode noise, with high frequency switching components. We must not just consider the motor frequency when we're talking about accuracy of an instrument. We need to consider the full spectrum and what power components are where in that spectrum in order to get a greater picture. So let's have a look. So here is the point where we measure the input of the AC drive. What we got here is a breakout box. This is an N4L designed breakout box and makes it very convenient to take out the voltage connection, which we can see here, and to take out the current measurement just there. And we're measuring the internal, using the internal shunt on the PPA1500 power analyzer. It just makes a very convenient and safe method of measuring input power to the device. So basically what we have here is the input voltage and current measurement, and of course power measurement of the AC drive. Now the AC drive is currently in standby mode, connected to the mains, but the output's off. What we're measuring here is, as you can see, the voltage of 248.3 volts. That's UK mains voltage, approximately 50 Hertz and 44 or so milliamps. You can also have a look on the scope, quick look at the voltage and how peaky the current is. So typical sinusoidal voltage, slightly flat top, typical of mains throughout the world, and a very peaky non-PFC current waveform. It's important here that we consider the wideband current accuracy, not just 50 Hertz, because there are power components and a lot of harmonics, if we look at the harmonics quickly, of that current, so considerable distortion on the current waveform, about percent on the voltage waveform. If we look at that graphically, we can see a significant amount of current distortion in the harmonics there. Let's go back to power. Now, let's just discuss why we've chosen the 1500 for this measurement. Now, one of the main reasons is that the AC input measurement, providing that 0.1% nominal accuracy is okay for your application, then the input side is actually a simpler signal to measure. Although there are challenges, as we discussed with peaky wide bandwidth current waveforms, primarily that it's not as complicated as the output signal, and at times when accuracy is not required of the very high accuracy instruments, then the PPA1500 or even PPA500 would be adequate for the input side measurement, whether that's the DC bus or the AC input signal before the DC bus. Either way, the PPA15 can provide a very good measurement, synchronizing to the 50 Hz, providing very good dynamic range on such a signal. And what we can do is then synchronize both instruments within our software program, PPA log, and I'll show you that later on in the video, in order to perform an efficiency measurement from input to output. Now this is up to the engineer to decide whether the input accuracy of 0.1% is adequate, and of course we offer 0.01 nominal accuracy on our top instrument, which can quite equally be applied to the input signal. But there's a cost implication there, and it's up to the engineer to decide whether that's worthwhile for them. So what do we need to do in order to get a good measurement of the AC input signal? Well, the simple answer is not much with the PPA1500, because it's perfectly well set up to provide good measurements out of the box, I suppose you could say. Now, a couple of things to consider, as always, whenever we perform a power measurement, is we need to look for the frequency first. Is the frequency correct? If the frequency is what we expect, most likely the rest of the measurement's going to pan out just okay. Now on the voltage and current side here, we're using the internal voltage attenuator and the internal current shunt. Now if we look in the range menu, you can see I'm using internal, and I'm going to allow the power analyzer to range up and down as it wishes. Now if you were doing an inrush measurement, for example, and you wanted to measure how much inrush current there is to the device when we either first plug it in or when we turn the output on, then we'd look at the range up only and run the test a couple of times in order to range up to the top range, and then we leave it on the top range so that we're not ranging during an inrush test. What I'll do is in a later video take you through how to measure inrush current with a power analyzer. But for today we want a steady state efficiency measurement, so let's leave it like that. Now of course what we've got here is, due to the fact we perform a real-time DFT, what we have is total and fundamental separated, real-time, live during the measurement. What that means we can achieve is we can separate the total wideband RMS signal, so we've got 46.0 or 46.1 milliamps wideband, and then we've got 15 milliamps fundamental. So what that means is the 50 Hz or the 49.936 Hz component of that distorted current waveform is 15 milliamps, whereas the wideband RMS is 44 milliamps. So there's a big difference, hence the large distortion. Now here, what we've got, very similar numbers. That makes sense because in the harmonic menu, you can see that there's very little distortion to the voltage, which gives us an idea that the wideband RMS is going to be very similar to the fundamental, which is at 50 Hz, which is the case, only a volt different, so very little distortion there. Now, although we've got a distorted current, we actually have most of the power at the fundamental. So that's something to consider. Just because we have current wideband, it doesn't mean that we're going to have power wideband. Okay, so one other thing to basically take note of is in the acquisition menu, what we can do is set up the instrument to be optimized for our setup. Now, normally you would probably purchase a single phase analyzer if you're only going to be doing single phase input measurements, but on this occasion we're actually using three-phase analyzer for a single phase application at the input. So what I'm going to do is change it from the default three-phase 3 watt meter to the single phase 1, and also I'm going to change the speed because the medium update rate is okay, but I want a bit faster measurement today. So let's move it to fast initially and see how we get on. Everything else can stay as standard. There's nothing else to change for a 50 Hz, 240, 250 volt internal shunt measurement. If we were using external shunts, then we would need to go into the range menu, set up the external shunts. but I'll leave that for another video and separate that from this tutorial. Okay, so let's just have a quick look at the inverter drive before we move on to the output waveforms and setting up to measure pulse width modulated waveforms and power. Okay, so what we've got here is a Mitsubishi Electric AC input, AC output, single phase in to 3-phase out PWM motor drive inverter. So it's a frequency converter, and that's going to be driving a 3-phase motor at the output. So we are, of course, just a quick reminder, are going to be measuring the AC input and the AC output, and comparing those powers and looking at the electrical efficiency of this device, including losses in the rectifier, across the DC bus, filtering, and at the PWM inverter output. So switching losses will all be included in our measurement, and we'll now look at how to set up the analyzer for this device. Now, this device has a variable switching frequency, but today the switching frequency is going to be set to approximately 8 kHz, and that's one of the most important points to remember when you're going to be setting up an analyzer to measure an inverter drive, because the switching frequency is what we want to be filtering out in order to lock onto the frequency. However, it's vitally important not to filter out the high frequency components of the power measurement. Now, what the N4L analyzer is capable of is performing parallel filtering. So what that is we are basically taking the data down 2 paths, and we're filtering out the high frequency component of the voltage signal in order to lock onto that fundamental of the voltage, and then we're taking the wide bandwidth data down to the processor or the DSPs for the power measurement. So we're always getting a full wide bandwidth power measurement and power result. However, we're able to lock onto the voltage fundamental signal. So for example, when I say fundamental, I mean the motor frequency. So we could have a motor frequency today of 80 Hz, but the switching frequency is 8 kHz. Now we want to be locking onto that fundamental, because most of the power, of course, is at the fundamental frequency. So we want to be locking on to that fundamental frequency, not the switching frequency. And that's the most important point. So let's move on to setting up the analyzer, looking at some waveforms. Let's initially turn on the device. Turn that on. Standard frequency default, well, here is 31 Hz. So I'm going to leave it at that, and we'll set up the output in order to measure a 31 Hz motor frequency, remembering we have an approximate 7 kHz switching frequency. Right, so what we have here is the output of the AC drive, and we can see the 7.4, 7.3 kHz switching frequency being locked onto. The reason for that is because the instrument's just in default settings, so we're going to go through every setting required in order to get a reliable, stable and accurate PWM measurement of this drive. So a power measurement of this drive. Let's have a quick look at the scope. It's always good to look at the scope because we want to have a look at what's going on, check we've got waveforms on each channel that we expect. So we basically we've got the PWM drive, voltage waveform at the top, and the current sinusoidal with noise spikes at the bottom. Due to the fact that there's noise spikes, it's important to exhibit good common mode rejection because we're measuring a very small differential voltage across a very small impedance, which is bouncing around, as we call it, bouncing around at high voltage here, so at high frequency. So it's important to be able to reject that common mode voltage across the differential measurement across the shunt. Now, just check phase 2 as we expect, phase 3 as we expect. So I'm happy that we are looking at an actual signal there. Now, what we've got here, of course, is 7.5 kHz. So let's have a look at locking on to the correct frequency. And what we want to do is go into the application mode here. and we change the mode to PWM motor drive. After we select a mode in the PPAs, what we always do is go down to the next line, default settings, press enter. And what that basically does, it selects some suitable settings in the background optimized for PWM motor drive measurement. Now, as we discussed, the switching frequency, approximately 7 kHz, and today our uppermost motor frequency measurement is going to be around about 100 Hz. And the rule of thumb here is to use a frequency obviously in between the switching frequency and the motor frequency, but I always veer closer to the motor frequency. It just gives us better frequency synchronization. So if I select 250 Hz, which is well above the 100 Hz uppermost motor frequency and well below the switching frequency, what we have here is frequency reference. Now we can choose to synchronize off the voltage and the current. The benefit of synchronizing off the voltage is that the voltage signal is always there, even when there's a very low current signal. So it's sometimes better with the intelligence of the parallel filtering option that we've got here to use voltage. We can also use speed, of course, from a speed transducer. And low frequency mode. Now this is a mode that sometimes confuses users, but what this means is that I've got here by default a minimum frequency which gets enabled when low frequency mode came on, minimum frequency of 0.5 Hz. Now what that means is that the analyzer will continue to look for a frequency until the 0.5 Hz point, after which the analyzer will assume it's DC and show 0 Hz on the screen, on the display. So if you are never going to go below 5 Hz, set the minimum frequency to 5 Hz. Anything below that can be considered DC. It's just so that the instrument doesn't sit there waiting forever, because the lowest possible frequency that we can detect is 10 millihertz, which is a long period there, long fundamental period. And of course you need one cycle before you get an update on screen. So if you're at 1 Hz, the maximum update rate for the analyzer is going to be 1 second. So we need to talk about that. Now, the talk of speed aren't going to be used today. If we did enable them, what we can choose is an analog version of both, a pulse torque, pulse speed, or pulsed versions of both. So if we had analog, for example, we can set how many Newton meters per volt we have there, an offset for the torque, and a speed per volt, so an RPM per volt, and an offset for the same. But let's turn that off. Efficiency. Now we're not going to display efficiency on screen because we're going to do it via software. But you could display efficiency as, for example, sum over phase 3. So there's a method of using the third channel as the AC or the DC bus. So the AC input or the DC bus. And you can also measure the sum on phase 1 and 2. So the 3-phase power is measured on 1 and 2, and the DC bus on channel 3. Or we can do master over slave, so we could do 3-phase input to 3-phase output with 2 3-phase analyzers. But today we're going to disable it because we're going to do the single phase from the PPA1500 through software, and the 3-phase output via the same software program. We'll show you that in a short while. So, PWM motor drive mode enabled, 31 Hz. So I'm scrolling through now with the enter next button so I can look at phase 1 power, phase 2 power, phase 3 power, sum power, 19 watts, okay, synchronized perfectly to the 31 Hz, 135 volts, 198 milliamps. Now, what we do need to look at here is how we've now got kind of like what we had, an opposite of what we had on the input power. So we've got 198 milliamps current total, 190 milliamps fundamental. so very similar. So it's very likely that the distortion is going to be low, and on the scope we can see a sinusoidal, somewhat sinusoidal current waveform and a very distorted voltage waveform. So we'll see here that the voltage wideband is 136 volts, but the fundamental component at the 31 Hertz is only 89 volts. So we've got a lot of distortion on the voltage there. Now, the reason the power is similar but not the same. So we've got 6.8 watts on phase 1, 6.5 on phase 2, 6.6 on phase 3. Let's look at total. So we've got 20.01 watts total power wideband, but we've only got 19.28 watts fundamental. So we are using the discrete Fourier transform to separate the fundamental from the total, and we can see that we've got, what's that, over 0.7 watts of wideband power somewhere else in the spectrum, not at the fundamental. Now that's something that's sometimes very interesting during a power measurement, to know whereabouts the power is, whether it's at the fundamental or whether it's at the on wideband. So if we have a quick look at the acquisition menu, we can make the similar change to what we did on the input analyzer. So we're setting the windows to the same size as fast. All of the settings can stay the same. Now, just a quick example, if I wanted to use the current as my frequency reference, I can, and we'll get a similar result. However, I like to leave it as voltage, because it means that as that current gets really low, as the load goes off, we've still got a voltage there and we can still extract the fundamental with the DFT. Now do note that this is still a wideband measurement. Just because we have a 250 Hertz frequency filter for the frequency synchronization, we are not putting the filter in there for the wideband power measurement. Now if I can apply an inline digital filter of, for example, 1 kilohertz, and this filter is in phase, okay, is in line, sorry. Now this is sometimes used in other applications where we genuinely aren't interested in the wideband power. I'm just using it here to demonstrate how some other analyzers on the market will have to filter the signal itself in order to lock on to this noisy frequency, fundamental frequency. Now let's see how that affects the numbers. What we can see here, as you can see here, that's brought the RMS voltage right down. Let's look at RMS power, 19.4 watts total power now, 89 volts now. So we're narrowing the bandwidth of the instrument. Now even if I narrow that bandwidth down to 5 kilohertz, we still got very much a sinusoidal voltage, which is obviously not the truth, but this sometimes does highlight and how you can cross-correlate with older technology which cannot perform this parallel filtering approach. So we have 91 and 89 as opposed to, turn that off, which means we get the full wideband frequency, we have 135 and 89. And by default we've gone to 200 kilohertz. I could go to 2 megahertz just as fine and achieve frequency lock, and 137 volts, 89 volts. So that's the 2 meg bandwidth of the instrument showing there. Very stable, no problem. Now what we can do is, of course, I'm going to go and change the frequency on the motor now to something like, let's try 60 Hertz. And we can see the frequency tracking. Now this is a really nice feature of the PPA5500. We're able to track frequency as it changes, and we'll also be adjusting real time the size of the acquisition window. Okay, so it's not a fixed window. This instrument is synchronized to the fundamental frequency. That's how we achieve such phenomenal high frequency accuracy. So you'll be able to change and track the window as the frequency changes. We're going down to 35 Hertz now. We can see it track nicely to 35 Hertz. And it tracks no problem whatsoever. So if you are doing some dynamic testing, then the instrument is able to track that dynamic change without a problem. So just a reminder that we are using internal ranges, so we didn't have to change the ranging. That's sometimes needed, especially in the electric vehicle market where currents are in excess of hundreds of amps. So we sometimes need to use external shunts here. That will be in another video. Now, what I'm going to do now, I want to compare the output power, which is 21 watts, to the input power, which you can't see on the video right now, but that's 27 watts. Okay, so we've got 27 watts in and 21 watts out. What I'm going to do is I want to compare this in PPA log software. That's the Newton's fourth data logging software. So I need to make sure that my comms are set up for the medium I'm going to use. I'm going to use USB, which is fine, and you won't be able to see this, but I'm just going to make sure the other instrument's in USB, which it is. So now we are ready to connect to the software and perform an efficiency measurement from single phase input to three-phase output of a PWM motor drive. Of course, this is off-load, so there's not going to be fantastic efficiency, as you may have guessed from the 27 watts in to the 21 watts out, but it's going to be a very accurate efficiency measurement nevertheless, using two different models within the range of power analyzers. And I'll show you how that's no problem interfacing the two together. We don't have to have two PPA5500s connected together, for example. We can mix the models. So let's have a look. Once connected to the instruments, we test each connection. If the connection is successful, we click the connect button. The multi-log menu is used to select the parameters we wish to log. We select phase 1 frequency in watts on the PPA1500, the input power, frequency in some watts on the PPA5500, the output power. We then use the equation editor to create our efficiency calculation, giving it a title in the process. We select the input power on PPA1 and the output power on PPA2. We then create our watts out over watts in multiplied by 100 efficiency formula. We then save the equation. Re-entering the multi-log menu, we select our efficiency calculation. Our efficiency calculation is then shown on the bottom left on PPA1. We change our update rate. We want an interval of 500 milliseconds. Pressing the start button initiates the log. We can see the data coming in 500 millisecond intervals. The graphical display provides an intuitive view of the behaviour of the device under test. We can select the parameters we wish to view. In our case, we have selected frequency and watts on PPA1, frequency and some watts on PPA2, the output power. We can enlarge the display with the View Full button. As you can see, we have an efficiency figure of 76.6%. This is expected as the motor is off-load. After stopping the log, we have the option to export to Excel. Doing so presents the data in table format with colour-coded headers, making interpretation easy. This tutorial has demonstrated the use of the PPA1500 and PPA5500 for 4-phase power analysis. The same instrumentation could be used for power analysis up to 12 phases. Utilising multiple 3-phase instruments provides flexibility and increased processing power. Thank you for watching, and see you next time.